In the last class, actually, we had discussed about the frequency response of common source amplifier. I'll just brush up the same thing just before going to we discussed the general frequency response and then we moved on to the high frequency response. So, okay. So, the frequency response of common source amplifier is something like this. This would be the general frequency response, as you can see. So what we usually assumed, we assumed it would be a constant, that this straight line here in the midband, whatever we would get it at all frequencies whenever we analyzed amplifiers. But that is actually not so. So what we saw was, in the low frequency region, there is a decrease in gain. And also in the high frequency region, there is a decrease in gain. The gain doesn't remain constant at low as well as high frequency regions. And the main reason for that is the low frequency region, the external capacitors like our coupling capacitors CC1, CC2 and the bypass capacitance CS. All those three capacitors play a significant role in the low frequency region, this region. So that's why they tend to reduce the gain at low frequencies. Whereas in the high frequency region, the device capacitances, that is CGS, the gate to source device capacitance, which comes internally in the MOSFET at high frequencies, and the gate to drain capacitance CGD, both of them will play a major role and they tend to decrease the gain at high frequencies. So please remember, low frequencies means external capacitances which are connected in the amplifier circuit will decrease the gain. At high frequencies, the internal capacitances of the MOSFET will decrease the gain. At mid frequencies, the low these capacitances, whatever capacitances we have here at mid frequencies, they all will be please mute your sounds again. And please remember, this is recorded and it will be shared. If something wrong happens, last times also they are monitoring and we'll be punishing the person whoever is trying to do mischief. So please take care, you don't involve in unnecessary things. So if you have any doubts, you can raise your hand. I will surely try to clarify your doubt. Okay. So you have different options where you can show your reaction. Use that reaction button and you can raise your hand or anything. Please remember. Okay. Whenever you have doubts, you raise your hand. Please mute your audios. Again, I'm telling. So now let's consider, we said, so in the mid frequencies, what happens? The external capacitances will be acting like short circuits. The device capacitances will not be there. They want, in the sense, they are very low in value. We can consider that they don't exist. So in the mid frequency band here, we get the highest gain in any amplifier. Okay. And the useful range of frequencies for operation of any amplifier, we call it as bandwidth. So that bandwidth will be computed between the lower cutoff frequency FL and the higher cutoff frequency FH. This lower and higher cutoff frequencies are computed by considering half power points or the points which are 3 decibels below the midband. So the midband gain, if it is AV, if I come down by 3 decibels, if it is AV in decibels, AV minus 3 dB, say it is 100 dB in the midband, at 97 dB, I'll draw a straight line and wherever it intersects this response curve, yes, wherever it intersects the frequency response curve, there we will, so wherever it is intersecting, that we will consider as the FL and FH point. In the lower end, it is lower cutoff frequency FL. At the higher end, it is upper cutoff frequency FH. So we discussed all these things. So the bandwidth is FH minus FL. That is the useful range of frequencies for operating an amplifier. Then we discussed the high frequency response. Since some of you told you didn't follow part of it, I'll just brief through this quickly. So the high frequency response, we are considering the midband and the region after the midband, the frequencies after the midband. So to analyze the behavior of this amplifier in this region, especially after the midband, the region where FH occurs, the high frequency cutoff, we'll try to analyze the behavior and find the gain of the amplifier in this region, for which we will have to consider the high frequency equivalent model of the MOSFET. We have considered this high frequency equivalent model, okay, and you can see the device MOSFET has two main capacitances, between one is between gate to source, the other is between gate to drain. So this gate to drain capacitance, though it is small in value, it connects the input to output, hence it will get multiplied by the gain factor of this, so it will have a major effect, okay. And as usual, on the output side between drain to source, we have the dependent current source in parallel with the output resistance R0, the drain resistance RD, and the load resistance RL. On the input side, we have the signal generator VSIG having a source resistance RSIG and the bias resistor RG. So to analyze the behavior of this circuit, we are considering, please remember, the high frequency response. Only when I consider high frequency response, this device capacitances CGS and CGD will come into picture, and we have to consider this high frequency equivalent model of MOSFET. Low frequency model will not have these two capacitors. These two will be absent, okay, in the low frequency model. So the equivalent circuit of this can be simplified by considering all these three parallel resistors together as one single resistance RL dash, as you can see here. It's a single resistance RL dash, which is R0 in parallel with RD in parallel with RL. And then we have done Thevenin's theorem on the input side, in the sense I am using all these three elements, I am clubbing. I am trying to find what is the resistance from gate to source terminal by shorting this source. So that's how we apply Thevenin's theorem. Applying Thevenin's theorem means short the voltage source, find the equivalent resistance. So this will be RSIG in parallel with RG. That's the Thevenin's equivalent resistance. See here, we have connected it here. The equivalent resistance between the gate and the source. And after that, we found the equivalent voltage VGS, the voltage drop. So the voltage drop here from gate to source, it will be using voltage divider VSIG into RG by RSIG plus RG. Okay, so that's what we have considered here. VSIG dash, we call it as VSIG into RG by RSIG plus RG. Okay, so this is the simplified equivalent for the actual model. So once we have this simplified equivalent circuit, we have to analyze this circuit. So please remember this circuit. In that circuit now, the first part, I have to find the mid-band voltage gain. What happens to the voltage gain in the mid-band? Please remember, in the mid-band, the external capacitances will also have no effect. The device capacitances will be absent. This CGS and CGD will not be there. So you see, in this equivalent model, I have considered the small signal equivalent model which we had taken before. We have analyzed this model before. Okay. So to find the mid-band gain, I should use the earlier circuit which we have used to analyze a common source amplifier, where our coupling capacitances and the bypass capacitance will be acting like a short circuit, and these device capacitances will not have any effect. They won't be present. So what was the earlier model? You had a bias resistance, you had the signal source, at the output side between drain and source, the dependent current source in parallel with all these three resistors. So this will be the model which I have to analyze for mid-band voltage gain. So what would be the value of V0 in this circuit? As you can see, it's written here. The voltage V0 would be this current GM-VGS into R0 parallel RD parallel RL. All these three put together, remember we had considered it as what? RL dash. All these three together we called it RL dash. So what is the value of this V0? The value of V0 would be minus GM-VGS into RL dash. And what would be the value of VGS? We already said VGS is the voltage here. It is equal to V sig into RG by R sig plus RG. So the value of VGS, see here, V0 is written. It is minus GM-VGS into RL dash. And RL dash is R0 parallel RD parallel RL. And VGS here, for VGS here, we will be, sorry, for this VGS, for this VGS, I will consider the voltage across this RG, which is V sig into RG by R sig plus RG. See here, V sig into RG by R sig plus RG. That V sig, if I take it to the left hand side, I can get V0 by V sig. Remember, this is V0. And in V0, I will substitute for VGS like this. RG into V sig by RG plus R sig. When we substitute that and I take V sig to the left hand side, I'll get the ratio of output voltage to the signal generator voltage, which is nothing but minus RG divided by RG plus R sig into GM RL dash. Okay. So this would be the mid-band voltage gain. Please remember, AM represents the mid-band voltage gain as shown. Next, let us try to let us try to consider the high frequency gain. So I have considered, yes. Hello, Amok. You have something to ask?
No, ma'am.
Okay, please mute your audio. If you don't have anything, please mute the audio. Okay, so now after seeing the mid-band gain, we have come to the high frequency response. So I have used the high frequency equivalent circuit, this circuit, where CGS and CGD come into effect. So this was the simplified circuit which we wrote here. You see here, we have from this actual circuit, we got this simplified model, and from this model, we have to analyze what is V0, and we should find the ratio of V0 by V sig. Okay, then I'll get the high frequency gain. To do that, first let's find the value of current IGD. We said the gate to drain current is given as what? The difference in voltage between the gate and drain terminals. This is the gate and this is the drain. So this is the drain terminal and this is the gate terminal. And what is the difference in voltage? Here I have VGS and at the drain I have V0. So the voltage drop across this capacitor is VGS minus V0. Okay. And what is the reactance of this capacitor? It is 1 by SCGD. So how do I find the current? Current is voltage by reactance. So the value of current IGD will be VGS minus V0 divided by 1 by SCGD. 1 by SCGD is the reactance of this capacitor CGD. Okay. So when I have this, that SCGD will shift to the numerator and you'll get the value of current IGD is SCGD into the voltage VGS minus V0. And don't we have the value of V0 already determined? V0 is found as minus GM RL dash into VGS. We already found this voltage, the midband voltage. I'll substitute that V0 value here. So minus of minus, this becomes plus. So the value of the current through this capacitor is SCGD into 1 plus GM RL dash into VGS. Okay. So next, we have X and X dash here.